I did my very best. So let's start this talk, and let me introduce Harald Welte. He is talking about some examples of smartphone hardware and his efforts to dissect them and analyze what's done. So please have a nice welcome to him. Yeah.
Hello everyone. Thanks for the introduction. I'm very happy to speak here at, I think, what must be the 11th CCC Congress that I'm attending. So if you didn't manage to grab a seat and you have to stand, I can offer you as sort of, well, I have to stand by myself as well, so. Anyway, yeah. As the introduction said, this is going to be a talk about smartphone hardware. As many of you know, I have been involved with OpenMoko for some time. But this is not an OpenMoko talk, just to be precise. I mean, OpenMoko is one example. There's going to be more examples, and I will talk fairly generically about how smartphone works. So this is just my usual slides about what I do and what I have been doing. With regard to mobile phones, I first really got in touch with doing anything mobile phone related in 2003 when, while doing my usual GPL enforcement work, I was having problems with a certain Motorola phone that had Linux, so I started to get interested in the phone. Before that, phones, I don't know, I rarely use the phone anyway. So, well, then I started OpenEasyX because we wanted to have a proper open source distribution for the open source Linux system on those devices, and there were more and more devices coming out in this, what Motorola calls EasyX architecture. In 2006, I had the opportunity to buy a GSM-based transceiver station, which is something that I'm going to talk about tomorrow. I've been working for OpenMoko as a lead system architect that includes both the hardware and the system level software for some time. And now, right now, I'm working on a project which I call GNUfish, which is about porting Linux to a certain series of devices manufactured by E10, designed and manufactured by a company called E10. Well, and right now, this is why I've just come up a minute before my talk. I'm working on running our own GSM test network in the hack center downstairs. See the talk tomorrow. So smartphones, what are smartphones? Unfortunately, there's not a very clear terminology. You know, oh, a smartphone is a phone that has email, but then how many phones don't have email today? It's not really a clear definition. So many people in the technical community, they say, well, a feature phone is something that has a single CPU, a single operating system, and where the entire GSM stack plus the user interface plus all the applications run on a single CPU. Those systems are typically extremely closed because certain commercial entities in the mobile phone market tend to be very closed. And thus, development of applications or additional applications for these kind of phones is very hard because they don't really want to run your code on the same CPU as the GSM stack is running. What I call smartphone, also for the remainder of this talk, are phones that contain two main processors, which is one CPU core that actually implements the network protocol, like the GSM, UMTS, HSDPA, HSUPA, and so on network, and another CPU core which actually runs the user interface and applications and so on. So what you can say basically is that a smartphone is something like a traditional old-fashioned GSM feature phone, which some people then also call GSM modem, and a PDA in one device, something like that. That's basically what you get. It's important for me to outline this, also as the idea why I came up with presenting this talk here at the CCC, is that even in the technical communities that I tend to meet people in, a lot of people were in the misconception of, you know, that somehow the network stack runs on the application processor, or that there's no real distinction. So that's very important to know that in smartphones there is this two different systems basically in one box, but they have a very thin communication interface and they're extremely independent of each other otherwise. So what kind of components do we have on the application processor side? That's going to be nice nerd porn in a couple of minutes with PCB photographs and so on. So There is an application processor, it's what people typically call it, AP, which in turn mostly is an SoC, a system on a chip. The main manufacturers here are Samsung, Marvell, TI, and Freescale. TI is TI OMAP, people might have heard about that. Marvell is called PXA something, PXA 250, 270, 300 something. PXA was originally the X-Scale design from Intel, which Intel sold to Marvell maybe some 2 or 3 years ago. Samsung has what they call the S3C 24XX and the S3C 64XX, and then they have certain undocumented components which they use in iPhones. You have some amount of flash. Typically, it used to be, or still is to some extent, single-level cell NAND flash. Multi-level cell NAND flash is coming up more and more. It's typically connected to the NAND flash controller inside the system on a chip, which means that this is native raw NAND flash. It's not like a solid-state disk that looks like a hard disk and offers a block device abstraction to you, but it's raw NAND flash, and your file system has to work, or your block translation layer has to work on top of that, because NAND flash has its inherent characteristics. You can't just use it like traditional block devices. So this is not like a USB drive. Oops. Sorry for that. Then you have RAM. Typically, it's still mobile SD RAM, but mobile DDR is becoming more and more an issue right now. So phones with DDR memory are not, are not unheard of. The mobile in the respective RAM name only indicates that there are certain features regarding power consumption, suspend, and so on. So, for example, there's things called partial array self-refresh, where when the processor suspends into RAM, you can refresh only half or a quarter of the RAM if that's sufficient. So you don't need to refresh RAM that's empty, because refreshing empty RAM just wastes battery. These kind of things. Also, the drive strength, like how many milliamps the actual interface is driven with, that can be dynamically adjusted, and they have all kinds of weird features to save the last couple of microwatts. You have a power management unit, and that one is typically fairly, not complex necessarily, fairly inclusive or fairly big, as in has lots of different functionality and features. Some people call it PMU. I think PMU is an XP or Philips-inspired terminology. Other people call it PMIC, which I think is more the TI and Wolfson speak. So PMIC is Power Management Integrated Circuit. They usually connect over I2C or SPI with your system on a chip device, and the power management unit typically includes something like, I've seen units up to 27 voltage regulators in a power management unit in a mobile phone. Somewhere between 11 and 14, I would say, is the average number of power regulators that you have. You also, some of them are switching, some of them are linear regulators. And the PMU also often includes an RTC or touchscreen interface, and then some minor peripherals like that. You have an audio codec for playback and recording of digital audio. Typically connects over I2C for the control channel, and over a PCM bus, sometimes also AC97, but not very common, for the actual audio data. And most devices obviously have Bluetooth, and Bluetooth is typically connected over UART, in rare cases over SPI. Wi-Fi typically connects over SDIO or SPI. SDIO is basically SD card interface, but not just for storage cards, but for general purpose I/O devices. SPI, I'm not sure how hardware savvy most people in the audience are. SPI is serial peripheral interface. I actually don't know what SPI means. Anyway, it's a 4-line interface where you have master in, slave out, and master out, slave in, and clock and chip select lines. Okay, well, these are the kind of things we see on the application processor side. If we go to the actual baseband side, the baseband processor side, BP, it's AP and BP. You have a digital signal processor, which does the RF baseband signal processing, so things like the modulation, the channel equalization, and so on and so on. But it also does the voice signal processing, so the actual speech encoding, decoding, echo cancellation, and so on and so on. You have a CPU that typically is ARM7 based. Now with the higher end 3G, 3.5G modems, it's ARM9. And that CPU only runs the GSM protocol stack and typically an AT command interpreter for an AT command modem interface. You also have LCM, which is, it's a LCD screen module and a keypad matrix interface, which is not used in the smartphones because the keyboard, if there is any, or the keypad, as well as the screen are connected to the application processor. But you know, semiconductor manufacturers, when they build these chips, then obviously a single chip should fit multiple applications, so you can go to higher quantities. So they see the same kind of chip in a feature phone where there's no application processor, and then you see this very same chip, you see it in a smartphone where you have an application processor. And then the peripherals like a screen interface and keypad interface, you don't use that, even though it's there. What you also have, obviously, is an RF power amplifier, actually not one, but multiple power amplifiers from multiple frequency bands, not rarely. The power amplifiers basically are in the send stage, so when you want to transmit something on the air, you have a power amplifier for that. There is an antenna switch, which typically is a MEMS SPST switch, which I don't know how many people can parse that. It's a micro electromechanical system, single pole, single thread switch. Then you have the ADC and DAC for the actual analog to digital and opposite conversion for both the analog voice data as well as, more importantly, the baseband side, which is the actual information that you transmit on air or receive from air. Now, how are those two interconnected generically? So this depends a bit on what kind of communication system this device is targeted at. For 2G phones, which is just GSM voice, circuit switch data, and GPRS, the connection between application processor and baseband processor typically is a UART, so it's just a serial line, maybe 115,000 bps, maybe 230, maybe 460, sometimes around 800 kilobits per second, but that's really high. 921 actually would be the exact rate. So in more demanding communication networks like UMTS and HSDPA, HSUPA, the UART is just not fast enough anymore. We have data rates of up to 7.2 megabits coming in. You don't want to squeeze them over, I don't know, a UART or whatever. So the interface that we happen to see here in many systems is a shared memory interface. Mostly implemented as dual-ported RAM. So you have a particular RAM that has two ports, one to the application processor, one to the baseband processor, and then you communicate over this shared memory region. The other option that we see in some devices, mostly the less tightly integrated devices, is SPI. SPI can easily run at 20, 25 megahertz, sometimes even up to 50 megahertz. If you transfer one bit with every clock cycle, then you can easily get way beyond the 7.2 megabits on that. There's no standard for the protocol on top of SPI, though. There's also no standard for the protocol on the memory interface. Some systems also use USB, but USB is really not the kind of interface you want to use in this device. It wastes way too much memory, and you have problems that it's a very master-slave kind of interface where the master, the USB host, has to enumerate the device before they can talk to each other. So what do you do in case your USB host controller, which is inside the application processor, is currently suspended, but you get an incoming call from the GSM modem? You somehow have to wake up. So you need some kind of GPIO or interrupt handshake to wake up the processor. Then the processor has to enumerate the bus. It can find its USB device and so on. It takes way too much time. So that's a very bad design, actually. Now let's look a bit at the audio interface. The audio interface is actually an interesting thing to look at because most people think, well, it's a phone. What's so complicated about the audio interface? Well, we have typically at least 3 analog outputs. There is usually a headphone jack for like earphones or a headset. There is the actual speaker that is points at your ear when you use the phone, the ear speaker, and the ringtone speaker, which is at a different location to play the ringtones or music for whoever wants to listen to music on these crappy speakers. And then you have 2 analog inputs, the built-in microphone and the microphone that is connected externally in the headset. Well, then you need to somehow connect the GSM modem, which I'm not sure what I would call most cases. I would just say in a number of cases it's analog, so they actually connect line-level analog audio or even microphone-level audio between the baseband processor and the baseband processor and the audio codec that's on the application processor side. This is obviously very simple because if you take an existing mobile phone chipset that's used in a feature phone, it already has the input and output of analog audio. So you basically just wire that to a sound card kind of device, which is the audio codec that is connected to your application processor, and you have it working, but then analog audio has all kinds of issues. So some devices have digital interfaces here at the cost of significantly increased software complexity, because then you end up having PCM buses that sometimes are clocked by the GSM modem, but sometimes are clocked by maybe the system on a chip and so on. There's all kinds of interesting things. In any case, even if the GSM modem uses an analog interface, you still have 2 PCM buses. So PCM, pulse code modulation, that's basically digital audio interface, a very basic one. You have one between the system on a chip and the audio codec. So this is like on your PC with a sound card, you have your main CPU, and the main CPU somehow has a sound card attached to it, and then there's some interface between your CPU and the sound card. And that interface could be AC97, could be Intel high definition audio in the PC side. It's just a different interface in the phone. But it's basically for playback of digital audio from the application processor into the analog domain, and vice versa. So the other PCM bus that you see is between the Bluetooth and the codec, because there are Bluetooth headsets, and the Bluetooth headsets transmit audio data, and that audio data in such a battery-constrained, low-power mobile device, you don't want to go from the Bluetooth chipset through the UART into your application processor, into software, and then from there send it out again to the actual audio codec. So that's why you have a direct PCM interface where the Bluetooth can talk directly to your audio codec. This is the audio routing diagram of the codec chip that's used in the OpenMoko, both of the hardware generations. So I'm not going to go into the details, but basically you can see my mouse pointer here. Like we have from GSM comes in here, for example, in RXP, RXN. The headset microphone is connected here. The handset microphone is connected here. And then you have various inputs and switches and amplifiers, programmable amplifiers, programmable mixers. Here you have the analog digital converters. And on the right-hand side, you have all the different outputs, like the earphone speaker, the headset speaker, and the earpiece of the handset. And each of those tiny little spots in that diagram, they correspond to something that software can configure. So if you map that to ELSA, which we obviously do in which OpenMoko, but we did, I'm still talking about we because I was there when it was done. So which OpenMoko obviously did, if you want to represent this properly in a contemporary Linux system, you want to have an ELSA mixer with all those controls. So you have actually 94 controls in the ELSA mixer on a phone, right? And believe it or not, it can get fairly interesting to play with these things, because suddenly, if you have full control of this, you can do things like play back an MP3 file and feed that into your GSM voice call, so play back something, or record from the call, or do all kinds of interesting things. But it's possible, it's there. And this is not particularly complex, right? So OpenMoko is just as an example. This chip is used in a number of different devices, and similar chips are used in all smartphones. So there's a lot on the audio side just for that. The digital part is not, like here on the bottom you have the PCM to CPU and to Bluetooth part. It's not, like all the details have been left out. So this is already simplified to some extent. So, which brings us to OpenMoko hardware. So I'm going to look at 3 different hardware products or product families. First one is OpenMoko because it's interesting for people who are interested in this topic but who don't necessarily work at a mobile phone manufacturer. Because everyone can study the systems and the circuits and the schematics because the schematics are available. Full schematics in quotes, well, detailed schematics, but the GSM baseband side cannot be there because of the closed nature of particular commercial entities in the semiconductor business for mobile phones. But that, like, if you want to understand the functionality of the phone, the baseband side, it's, you just look at it as a modem. It connects to a serial line, you get analog audio data in and out, and that's about it, what you need to care about it. If you look at it on a high-level, simplified diagram, how all this looks. So basically, you have the system on a chip in the center. In this case, what is used here, well, Samsung actually does, sometimes they call it S3C, sometimes they call it SC3. They don't actually know which one it should be called. So don't be surprised by that. So this particular component, it's one component that is 13 by 13 millimeters, and I think maybe 1 millimeter in height. I don't remember exactly. And in that single package, there is not only the system on a chip, but also the flash and RAM memory. It's what's called a multi-chip package. So you have multiple dies inside one physical package to save physical, what's called PCP footprint. So you save space on your board design. Then you have the number of controllers or interfaces externally. So there's a NOR flash chip, there's some more SDRAM externally because 64 megabytes is not enough for everyone. There's an I2C interface that connects to the power management unit over here. The Wolfson codec, which is the audio codec on the lower left-hand side. And then there is the mono amplifier, which is external to the Wolfson codec. There's another amplifier, so you can hear your ringtone even louder. Then on this side, we have the Calypso, which is the GSM baseband processor. That connects using a UART, the serial line, to the application processor. And to another UART, we connect the GPS module. I didn't talk about GPS before. Not all the phones have it, but those phones that have it, it's always connected to a UART, but not always to a UART of the baseband, of the application processor. Sometimes they connect the GPS to the baseband processor. I think the technical reason for doing so is because they don't have enough UARTs on the application processor. But it makes me extremely worried if the GPS is connected to the baseband side. And then I should trust the device, it's like, the GPS data first goes into the GSM modem where all the, deep secret GSM stack is running. And then the GSM data is forwarded to your application processor. So if you switch it off on the application processor side, is it really switched off, or does it still feed the location into the GSM modems? Anyway, so we have an SDIO interface which connects to a Wi-Fi module, and we have a USB connect. This is not true. Is it? Oh, yes, it is actually true. Yes, it is true. It is USB connected, the Bluetooth, in this case. Yeah, because we ran out of UARTs. There is another. There is another connection between the Bluetooth module and the audio codec over here, but the person who drew that diagram, obviously it's hard to draw a line all across the diagram, but it's the PCM bus between the Bluetooth and the codec over here. Yeah, we have an LCD controller that is obviously connected to the LCD, not disconnected, and there is, oh no, sorry, no, it's actually true. The LCD controller is not used, the built-in LCD controller of the SoC is not used in this hardware revision, but there is a graphics accelerator, in quotes, connected to a display module. This is the LCD display. And that one again has an SDIO interface which connects to the SD slot because, well, the SDIO controller here is used for the Wi-Fi interface. So you see the kind of problems. Your hardware interfaces are limited in number, you add more and more peripherals, so where do I move it? Do I shift it here, but then I lose this? Where can I connect there? Where can I connect that? No. Okay, this is that's the overview diagram. Now, if you look at the actual board, so this board, I choose this picture because the quality is better than the later pictures. This is an old version of the hardware. So this is not the device you will get when you buy an OpenMoko system today. This is an old design, and I just put this up there to see, so you can see how much, how tightly squeezed the BGA packages are, like in this area, for example, and how full the board is in general. So this entire section over here on the left-hand side is the application processor section. We have the system on a chip here. This is the one which does not have the integrated flash and SDRAM. So we have the flash here, SDRAM here, and the S-media here is the graphics accelerator. This one, the PCF50633, is the power management unit, which is the same that is used in the iPhone, by the way. We made NXP to open the datasheet, so I'm sure people can have creative uses for that. That's the Wolfson codec for the audio side, and that one, I think, is that's the audio amplifier over there. And the section which has the frame for the shielding cover over here is the actual GSM modem side. This one is the baseband processor, then we have the DSP over here, some flash and RAM in one package down there, and this is RFPA, I think, over here, basically. And we have the section here, which is completely covered, is the GPS unit that is separately shielded because GPS has very sensitive signals. So this is basically how something like this looks like. Let's look at some other hardware. The Motorola EZX hardware, which obviously has only one W, as I recognize now, has multiple generations. There is generation number 1, which includes the A760, the A768, the A780, and the E680. All of these devices are not very commonly known in the Western world. They're mostly sold in the Asian market. The only thing that ever was, I think, regularly sold in Europe was the A780. And the hardware of these devices is fairly well known because the schematics have leaked quite some years ago. So people have been able to study them. In those devices, all the Motorola devices, for example, we have a couple of key characteristics. One of them is that the audio is routed digital, so we don't have analog audio between the baseband side and the application processor side. It's PCM interface. All of these have at least one custom ASIC, which is not a standard component that you could otherwise use. It's the power management unit in those devices. What else is characteristic about Motorola? And they have a very weird, at least the generation 1 and generation 2 have a very weird interface to talk to the modem. They use USB with some additional handshake lines, and it's like USB with flow control over GPIO, something like that. It's really nasty. The generation 2 phones are a little bit more known, as in the actual devices are a little bit more known in the Western world. I think some of them have been sold in non-Asian countries. The schematics of these, for some of them, also have leaked, so the hardware is also fairly well understood. And then it's the generation 3 hardware, for which the schematics, unfortunately, I have not seen yet. Those include the E8, Z6, V8, and so on and so on. These are more current devices. In those devices, however, it's very hard to do any hacking by yourself because they have a custom smartphone on a chip component. It's basically a single component that includes the system on a chip for the application processor side, which is an ARM11. The system on a chip device for the baseband side, which is an ARM9. 2 DSPs. The analog digital converters for the baseband side, and so on. So basically it stuffed the entire system into a single chip. So this is a very custom component, so there's no documentation available because nobody uses it outside of Motorola, and so on and so on. So that's not a very hacker-friendly device. So the generation 1 uses a Intel X-Scale. At that time, it actually was still Intel X-Scale PXA272, I think. The power management unit they use is called Motorola PCAP. I think it's the Power Control and Audio Peripheral, PCAP. It's connected over SPI, and actually it's connected over SPI to the baseband processor and to the application processor. So you have 2 CPUs reading and writing to the same registers in the power management unit. It's a bit scary. Some of those registers can only be read or written from one side, but not from the other side. Yeah. The baseband processor is what they call a Neptune LTE, which, as I said, is connected over USB with some weird handshake lines. Generation 3 has the custom SoC, and a lot is unknown. If you know anything, there is multiple wikis and communities and whatnot that might be very interested in your knowledge. So one of the things, or one of the what kind of people are interested in the details of smartphone hardware anyway? It's, well, in the, let's say, in the free community or in the open community outside of the respective handset manufacturers, it's mostly the people who want to put Linux on their phones. And in those cases, the system ships with Windows Mobile or some other operating systems, and then the community try to replace that. There's one community called XDA developers, which is mainly focused on HTC's various touchscreen-based Windows Mobile phones. They had, it's too little developers for too many devices. The product life cycles are short, and you need to do lots of reverse engineering until you get something going, so the progress is mixed. What I have started to look at recently is the E10 Glowfish device family. This entire product portfolio, you can have them with QVGA, which is 320 by 240, or full VGA, 640 by 480 pixels, Edge or UMTS or HSDPA, keyboard or no keyboard, GPS or not, Wi-Fi or not. It's entire, like, you can have well, you can choose, pick and choose. The application processor in all of these devices that you can currently buy is the same. Well, the latest one is another one, but almost all of them is this one, which is by coincidence the same one that OpenMoko also uses. So the documentation and the Linux drivers and everything is there. So what I went through is basically reverse engineering of that hardware to some extent. I do not have the schematics. I just started to dig into it. They're very similar, as I said, to OpenMoko, which makes it interesting from the kind of Linux support side. But this is not a Linux talk, this is a hardware talk. So what they use as a Wi-Fi module is the Marvell 8686, which is the same family that is also used in the One Laptop Per Child project. So there's quite a community working with these. A Surf GPS chipset. Surf is by far, I would say, the most common GPS chipset vendor. And Cambridge Silicon Radio Bluetooth chip, which is also fairly standard. There's a CPLD, a programmable hardware device for the power management and keyboard matrix scanning. That one is sort of the only really big unknown component. And there is the Ericsson GSM modem that they use, which has a documented AT command set, but which is attached over an interesting way of using SPI, I would say. In a sense that the SPI master is the modem and the slave is your application processor. But sometimes, your application processor wants to talk to the modem, so you have to issue some handshake line like, hello, I want to talk. And then you get basically pulled by the modem. It's like, oh, yeah, now you can talk. Interesting. I mean, I think this is very typical for traditional cell phone manufacturers, right? They come from this is the cell phone. Cell phone is above everything else. So the baseband side is above everything else. The baseband side, is the master. It takes control of the communication. It takes control over the power management and so on and so on. And, that CPU, the application processor, this is just, it's just for displaying applications. It's not the actual phone part. And conceptually, if you come more from a, like, I don't know, open source embedded devices kind of background, then obviously, the application processor is the center of the system, and the GSM modem sort of is a peripheral. So this kind of perception reflects in a way how the hardware architecture looks like. There are some cameras about which I don't care. So I started this project, the status of the project, you can check that somewhere else. So the question is, how does one go about looking or understanding more of the various hardware in those systems? Well, basically you have a number of different approaches. Number one is take the actual board apart, take notes of the major components, see if you can find anything, like Google for the identifiers on top of the components, try to get the data sheets, try to put together how the device works. This is actually fun, and I think I've been doing this with every device that I bought in, I don't know, maybe the last 10 years or so. So you just take it apart and see how it looks like. Then another option, obviously, is to use if it's a Windows mobile device, the hardware reverse engineering tool called Harrod. And then there's multiple ways how you can try to find the serial console or JTAG test pads. And obviously you can also disassemble Windows mobile drivers, which, well, according to the European Union Copyright Directive, decompilation is not allowed, but disassembling is not decompilation, so it must be allowed. So how do you go about this? Opening the case and voiding your warranty is obviously a nice thing to do. Warranty labels you can always find on eBay and somewhere else on the net. So, yeah, this is the battery removed from the device, and as you can see, there is already some kind of connector here, or test pads. It's not really a connector, but test pads. And if you see test pads that are accessible from the outside of the device, and you can be sure there is at least a serial port and or the JTAG interface of the application processor on those pads. You just need to figure out which one is which. So, taking the device apart, well, the plastics and so on sometimes is a bit difficult, but you get the feeling for it after some time. After you remove the plastics, you get something like this. It's like, well, okay, I have 3 metal boxes. Great. Well, then you have to remove the shielding covers, which in many cases, fortunately, are snap-on shielding covers. So you actually, with a small screwdriver, maybe a scalpel, you can try to lift them. If they're soldered on, then you actually have to unsolder them or cut them open with the scalpel, which is what I did on one of my Motorola phones. So this is the uncovered application processor section. So we can again see the Samsung system on a chip in the center. This one is the CPLD, which they use for various peripherals like keyboard scanning and so on. Yeah, I think that's about it in here. It's all kinds of smaller components, nothing really important. Like this is the power supply kind of stuff. This is the HSDPA modem section. So this entire section is for. And if you think, oh, well, this is an HSDPA modem, yeah, but if you try to think what that device does, it's actually a miracle. As in, this is something that can receive and transmit on 7 different frequency bands, right? You have quad-band GSM plus tri-band 3G. And it speaks, what is it, like 3 or 4 different modulation schemes on those frequencies. It has power amplifiers for different bands and so on. So it's actually quite a lot of technology in there. For those devices like the RF3000 and the Sky whatever devices, you can actually find the data sheets if you Google for them. These are mostly the RFPA, antenna switch, all kinds of things like that. This section on the lower half is the digital baseband side. This is the flash and RAM chip and the baseband processor. Yeah, well, the backside is not as interesting. You can, as I said, Google for the various component identifiers, and then you might get an idea what those are and how they might be interconnected. Obviously, JTAG is always interesting. So if you can somehow get your hands on the JTAG interface, you can access the integrated debug macro cell that exists in every ARM processor. So you can do hardware debugging, you can single step through the code, you can take full control over the system from your hardware debugger. The question is, how do you find and use them? So the traditional method is, well, you look for the suspicious test pads on the PCB. Tracing the PCB traces on mobile phones, you can forget about that. You can do this on large devices, like maybe a Wi-Fi router or even larger devices, but on a mobile phone, no way. Typically 8-layer PCBs with very fine pitch, there's no way how you can, with your eyes, trace where the lines go. So trial and error is a good idea. Sometimes you might find schematics, which obviously then you know where they are. This is a Motorola E680 with the JTAG ports of both the application processor and as well, interestingly, the baseband processor connected. Well, yeah, just connect to the pads and try the different signals and combinations and see what happens. And luckily, there is now a sort of a more efficient method, because JTAG is a long shift register, and you have input, out, and clock, and you can try to shift data in somewhere and see whether the same pattern shifts out somewhere else a defined number of clock cycles later. So there is a JTAG Finder project in hardware called JTAG Finder, which Hunz from the CCC, I'm sure he must be hanging out somewhere here, has implemented. And basically, you connect all the pads at once. This is the debug connector of the Glowfish device, which in the battery back, which I was talking about. You connect it to the breadboard. You connect the breadboard. Well, there's a logic analyzer as well here, but that's not really necessary. You connect the breadboard to your ARM development board. No, an AVR actually in that case, and a microcontroller development board, and then you run the JTAG Finder software, which does the brute forcing, basically, trying to find the JTAG pins. And, well, interestingly, the device was able to find the JTAG chains, both for the CPLD as well as for the application processor. And as soon as you have that, as I said, you can take full control over the system. You can do anything. Run your own code, single step through the existing code, do anything. Serial console is another useful thing. I mean, anyone who's ever dealt with like OpenWRT or similar projects, it's always useful if you have the serial console to the device in question, so you can well, see what kind of debug outputs the developers left in the final shipping firmware image, and as well to see if there's any way how you can interact with the device. So Linux-based devices or Unix-based devices, I would say in general, in quotes, including like VSDs or VxWorks or whatnot. They typically have some kind of command line interface or console or whatever on the serial port. Oh, sorry for that. Yeah, the escape button is somewhat broken after I dropped this laptop. And escape exits the application. Where were we? Yeah. Yeah. So the optimized method, as I said, you can find out about that with the JTAG Finder. We found the JTAG scans, serial console. So the transmit pin of the serial console is typically very easy to find. If you have a scope, even a very, very old analog scope from the 70s or maybe even the 60s would do, because the serial port spins are so low. You just like you keep power cycling the device on and off and on and off and on and off, which usually means battery in, out, battery in, out. And every time you power cycle, you connect your scope probe to a different test pad. And at some of the test pads, you will see patterns that, well, you can calculate the speed of the signals on the serial line for any given baud rate. So you know it must be in a certain frame. And then asynchronous serial lines have a very typical pattern that you can start to see. And then it's like, oh, this is the TXT pin. And if you connect that pin to your serial port of the computer, you will already get the output of the data. The RxD pin, which is like data from your system into the device, is much harder because you can't automatically detect it. Typically, a nice guess is left or right of the other pin. Well, if you use some kind of resistor to make sure there's no short circuit, and you connect it to each of the pins and try to transmit some things. Sooner or later you will find it. In most of the cases, the number of test pads or whatever are fairly limited, so maybe it's like 30 attempts and then you have it. Don't forget to add a level shifter if you're using actual RS-232 ports. They have very different voltage levels than the voltage levels used in the device. As the other approach, which is not as hardware-centric, is a hardware reverse engineering tool. It's an executable program that you can run on Windows CE devices, and it has a control socket on TCP. You connect to it from a console program on your Linux box or other box. And then basically you can do things like show me all the, give me one event for every interrupt that you receive, and then you get all the kind of interrupts. And you remove the ones that are noisy, and then you start pressing keys or sliding the slider or doing this kind of thing, switching on and off your backlight, switching on and off your Wi-Fi, switching on and off your GPS, and you try to see what kind of GPIO pins or interrupts happen, or what happens on the device when some kind of external event happens. So you can learn more about how the device works. It supports a number of different ARM-based system on a chips, so you can do these kind of things. You can also load any of your own code and also load Linux into RAM and try to boot from that while the system is still in Windows CE. Yeah, you can use that. You find documentation on the net. I don't want to go into the details. Time is running quickly. Obviously, what you can do is disassemble the drivers. Before you can disassemble as in assembly language the drivers, you actually have to disassemble as in unpackage the Windows CE ROM files, which is a very unpleasant exercise. This is the kind of various tools and scripts I had to use for the Glowfish, which like spending a day in the hex editor and trying to figure out what they did. And then in the end, you might get the actual DLLs, or might be able to recreate the DLLs for the drivers, and then you can use IDA or any other disassembler of your choice and try to find out what's happening. These are the kind of drivers that I was looking at for the Glowfish project. By now, I think there is very little that I don't understand in that hardware. So how do you do that? Well, the DLLs are completely stripped. Windows drivers are data-driven, so you don't have many symbols or function names. So if you try to disassemble the Linux driver, it's very easy because there's lots of function names that get called that have meaningful names. But in Windows drivers, it's basically everything is read and write in I/O control. It's like, oh, well, great. And all the details happen in data structures, so it's much more difficult to take things apart. Luckily, there's API documentation on the internet, all kinds of interesting things in there. The registry of Windows CE-based devices also gives you all kinds of hints. For example, most of the drivers have some kind of registry keys, and they might indicate some operational parameters, like what kind of GPIOs they use or something like that. Yeah, and then we get to the various links to the various projects. Just have a look, check them out, and finally my thanks slide. So I suppose there will be some questions. We do have time for questions. Yeah, I could even demo some things if people were interested in particular demonstrations, but I think that we should probably rather do in the Hack Center downstairs. Recent developments like if you look at devices that are, like I indicated, let me just state that before we go into the questions. If you look at devices like the G1, the phone that, this escape button. Anyway, it was just a thanks slide. We can just leave it like that. No, there is actually a way how I can skip all that. Yeah, great. If you look at the G1, the HTC phone that Google now sells, at least in the US and maybe some other places, or you look at the iPhone to some extent, but actually even more so the G1, what we see are these smartphone on a chip devices. That's a term that I just came up with. I don't know whether it's somebody else uses that in the industry, but as I said, you take the entire system and put everything in a single component, and that is sort of the danger for people who would want to work with mobile phones. I mean, as in community people who want to do whatever kind of hacks on them. Because right now, if the application processor is a standard industry processor, a standard industry system on a chip, you can get the documentation for that. So you at least get, how do the peripherals work? What instruction set does it use? How does it access its various interfaces? But with these tightly integrated system on a chip, smartphone on a chip devices, that gets increasingly harder because suddenly the top secret, super whatever, proprietary whatever information that relates to the GSM modem that the companies believe is so secret and has to be so protected well, suddenly is extremely close to the application processor again. And therefore, any information about the application processor they fear might leak some information about their super secret GSM side, and then their entire business model would collapse for whatever reason that nobody else knows. So I see sort of, like, we can do this now with current devices, with devices of the last couple of years, but looking for the next couple of, 5 years, I think it will be really hard. Also because things like cryptographically signed images for booting, and yes, they can be cracked and so on, we all know that. But it's getting harder and harder every year to do hacking on phones. So I'm very pessimistic, and now I'll take questions. Thanks.
Yeah, I've got actually two questions. The one is, you stated very clearly that in smartphones we have the baseband processor and we have the application processor. But in terms of protocol, I mean the mobile phone protocols are quite good documented, and I don't see a really good reason why they should be separated. The DSP with the modulation, okay, that should be a separate processor, but couldn't be the functionality of the baseband processor and the application processor be merged to save one part, which would save battery power?
The battery power, I think, is not that much of an issue because you have a certain CPU load, and if you put that on a single CPU, just the load on that CPU increases. Now, what you pay, so there are parts of the industry who want to move that, and I can assure you that all the major manufacturers of cell phone chipsets have that solution in their drawer right now, but they're not really happy to put it out of their drawer. So what they do is basically use a hypervisor and virtualize, and you have different virtual domains for the baseband and the other side. The reason why they want to keep it separate, I think, is one of them is there are, I think, like 4 GSM stacks that have been written. So those 4 companies who license these in millions of units every year, they make tons of money of the fact that they have a GSM stack. And if you, how can I say, the more open you are with regard to putting it on a general purpose processor that is documented where people run applications on, people will be able to reverse engineer faster or to find out and will probably replicate what you have done, and thereby your profit margin might go down. You might not sell as many stacks anymore, or you might not get as much royalties, and so on and so on. The other thing is always, the operators, are afraid of their network stability and so on. But as you said, the protocols are open. Somebody who wants to build open hardware and wants to talk these protocols can do it. It's definitely not a problem to do. The reason why they want to do it, the handset manufacturers, is to save ARM core license royalties. It's not the battery power, but like every ARM core in these devices, and for example, the OpenMoko phones have 5 ARM cores, right? Wi-Fi has an ARM7, GPS has an ARM7, Bluetooth has an ARM7, baseband has an ARM7, and the application processor has an ARM9. And for each of these cores, there are patent and whatever royalties to be paid to ARM. And if you can reduce that number, you can save, $1 per license or whatnot. And that obviously is a big commercial aspect.
And another question, or maybe a statement, you said that the GPS module is connected to the baseband processor on some phones. Couldn't that be due to the fact that you want the GPS module be constantly active? Because on my OpenMoko I have the problem, if the thing goes into standby and I re-enable it, it takes 40 seconds for to get a fix, and then it goes in standby again. No. That's unrelated. The power, like how do you power, so the power hierarchy in devices is typically very different from the data hierarchy.
So you can very well have a device connected to your application processor, but keep it powered up while the application processor is shut down. There's no problem with that. That's a pure software and hardware design choice, basically. I don't actually know what.
Just one question.
Okay, one more question from the left side this time. Jake.
Hi, thanks. Nice pants. I'm curious what you think about things like Android and if we'll ever see a cell phone where we'll have something other than the GSM bridge. So it's kind of two questions. Instead of the AT bridge, we'll actually have access to the raw GSM stack.
I don't think in the industry this will happen, right? So if the community doesn't come up with something like that, it won't happen. In the last couple of years, there's been a lot of community projects that do research on one or the other part of GSM. I've been involved in a number of those. And the fundamental problem is that there's a really big lack of skills. Like the GSM protocol side, there are not that many people on the planet who really understand it, and those people all work for companies that don't allow them to talk about it or to work on something else that's not related to their company. Getting used to how all this works is, well, I think it's an interesting intellectual challenge. The initial GSM specification, when it was published, I think in the early 90s, was already 4,000 pages. I don't know how many pages this is by now. The pages are the specs are very well defined. You can read them, you can understand them, it's possible. If you're interested, try to do that. And there's nothing that prevents you from implementing a fully software-defined radio-based GSM or 3G handset on something like the USRP with GNU Radio or some other hardware. So it's just, people have to be interested in that, get involved, have to actually do some work on this. There's nothing that, like, especially for 3G. So 2G, the GSM side, still has the proprietary crypto, which has leaked. But in the 3G world, even the ciphers and everything are publicly documented. So every single bit of the entire protocol is documented. You can all write that in free software. There's nothing well, there's patents and so on, which, yeah. But at least technically, there's no reason why you could not implement everything in software and have complete access to all the bits on the lowest level. Okay, well, thanks again.